Hello everyone, my name is Raju Saran and today I will be teaching digital system, and today's topic is practical explanation and some few examination questions related to the simplification of Boolean functions. We have already studied about different logic gates, right? And logic gates are the fundamental building blocks of any digital circuits like smartwatches, computers, and any other digital devices. At first, let's talk about OR gate. Mathematical expression for OR gate can be represented as y is equals to a plus b, where all the variables can be replaced by any other variables like x, y, z, or alpha, beta, gamma, or a, b, c, d, whatever you like. But in standard form, we generally represented the output either using y or f. If the function is a little bit longer, mostly f is used to represent, for example, f is equals to a b bar plus a b plus something like that. And for output of the logic gates, generally y is used to represent the output. Simply it's a variable and you can use or choose any of the variables as you like. And if the inputs are represented by a and b, for OR gate, y equals to a plus b is the mathematical representation of OR gate. Similarly, y is equals to ab is the representation. Here there is implicit multiplication sign, right, similar to the mathematics. And this is the representation of AND gate. Similarly, y is equals to a complement is the representation of NOT gate if the input is a. If the input is b, the output will automatically change to b complement, right? That is easy. And similarly, y is equals to a plus b whole complement is the mathematical representation for NOR gate. You can easily understand NOR means the output of the OR gate is inverted. We can see this much part is the OR gate and here is the complement, so it becomes not OR, that means complement of the OR gate. Similarly, here you can see NAND gate, which means the output of the AND gate is complemented and not. Generally, a combination of these logic gates are used to build different kinds of circuits, especially combinational circuit and sequential circuit. We will learn further about those circuits in chapter 4 and chapter 5, but now let us understand what a combinational circuit is. In the screen, you can clearly see a logic gate. Can you tell me which gate is this? Yes, you are right. This is a NOT gate. Okay. And we can combine multiple gates to build a digital circuit according to our requirement or application. We can make adders, subtractors, multiplexers, demultiplexers, and many more kinds of circuits. Let us make one to understand the core concept. Now I have connected a AND gate at the output of previous NOT gate, right? I can add another gate, another AND gate, but here one thing is different. You can see one of the input is a, which is derived right from the previous input, and other output is b, which is derived from previous b. Okay, but in previous gate one of the input is a but another input is b complement, because the input for the first AND gate is coming from the output of NOT gate. Similarly, we can add another gate which can be OR gate. Okay, now let us derive the expression for this complicated circuit. Okay, here let's talk about first AND gate. Okay, let me write numbers. You please don't write this in examination. Okay, these are just for understanding. Okay, if the input is A, here comes A, here comes B complement because of that NOT gate, and the output of first AND gate would be A B complement. Okay, because AND gate multiplies both of its input, right? Similarly, for AND gate number 2, the inputs are A and B, so the output would be AB. Okay, now we know the OR gate, what the OR gate does. If this is one OR gate, if the inputs are A and B, the output would be A plus B. Okay, see, but here we can clearly see that one of the input to the OR gate is A B complement. Just follow the wire. Okay, and other input is A B, so the output would be definitely the sum of both the inputs, which I have written here. Okay, the output would be sum of both the inputs. Here we can clearly see one complex Boolean expression, and this is the output of our combination of logic gates. And here in the final output, we can clearly see that variables are first ANDed. You can see here is also ANDing happening, and here is also AND operation happening, and the resulting terms are OR together. Here is a product, here is a product, and in between there is a sum. This is called sum of product. This is very important concept, and we use this term so many times in future. And AB bar is called mean term. AB is also called mean term. We can also write A bar B bar is also mean term, and A B is also mean term. Similarly, X Y Z or X Z Y and Z complement, this kind of terms where there is only product or AND gate, then those are called mean terms. And notice something important: in mean terms, each variable appears exactly once, either in normal form or complemented form. These are all valid mean terms. Each mean term represents exactly one row of a truth table where the output becomes 1. Suppose f is equals to A complement B. Now pause the video and think when the output is going to be only 1. You can build a truth table if you want. What was your answer? You can write in the comment. Okay, now we can clearly see that there is an AND gate in between the A complement and B, right? And AND gate's output is only 1 when both the inputs are high. That means one of the input, which is A complement, should be 0, and other input B should be 1. I'm sorry, the A should be 0 and B should be 1. Okay, since there is a complement, the 0 is converted into 1 by that complement or inverter, and input to the gate would be 1 1, so that the output will become 1, and no other combination works. You can try any other combinations if you want. Therefore, A complement B corresponds to exactly 1 truth table row. That is why minterms are called the building blocks of SOP expressions. SOP means you can think of a minterm as a unique key. The key is designed to open exactly one lock. Similarly, a minterm matches exactly one input combination, no more. भन्नाले कस्तो भन्दाखेरि एउटा मात्रै कन्डिसनमा चाहिँ त्यो हाई हुनसक्छ, अरू कन्डिसनमा चाहिँ हाई हुँदैन. मतलब चाहिँ त्यो एउटा मात्रै कन्डिसनमा म्याच हुन्छ क्या, अरू कन्डिसनमा जहिले पनि फल्स हुन्छ. There is also a standard for minterms numbering, and for two input variables A and B, the combination of two input variables can be 0 0 0 1 1 0 and 1 1, and minterms are generally represented by small m0, m1, m2 and m3. And for two inputs 0 0, the minterm is A complement B complement. Where there is a 0, you will add a complement to that variable. So similarly, there is also B complement. Similarly, for second combination, the minterm is A complement B, because the value of A is 0, so we write A complement, value of B is 1, that's why we write only B, not the complement sign. Okay. Similarly, for the third combination, there is the value of AB is 1 0. That means for 1 we only write A, and for 0 we write complement, because the value of B is 0, so we write B complement, right? So final combination, there is 1 1 for A and B, so we write AB. There is no complement sign. The subscript corresponds to the binary value. 0 0 means 0, 0 1 means 1, 1 0 means 2, and 1 1 means 3. And similar thing happens for three variables. For example, if there is C as a third variable, we have to add C or C complement according to the value of C, either C equals to 0 or C equals to 1. Now let's write the minterm for our previous gates. This one, for this circuit, the output was A B complement plus AB, and this is in sum of products form, right? This is in SOP form, and for SOP we can write minterms. So there is AB complement. Where can we find AB complement? Here, and corresponding value is 1 0. 1 0 means M2. Similarly, there is AB. Here you can see AB, and corresponding minterm is M3. So generally we represent this circuit by, if the output is F, then we can write, and if the variables used are A comma B, we can write minterms as summation small m and the corresponding binary values 2 comma 3. Okay, this expression and this minterm representation means the same. You can either be asked in examination to reduce this expression or reduce the minterms. Both means the same thing. Okay, we will further learn about minterms and maxterms in future lectures. Now let's continue to learn what maxterm is. Okay, a maxterm is just opposite concept. A maxterm is an OR term. Previously, the minterm was all about AND term, ANDing. There was product. But in maxterm, there are only OR terms, no AND terms. A maxterm is an OR term containing every variable exactly once. For example, A plus B or A plus B complement or A complement plus B or A complement plus B complement. These are the max terms. Each variable appears exactly once, therefore these are valid max terms. A max term corresponds to exactly one truth table row where the output becomes 0. अघि नै कस्तो थियो भन्दाखेरि मिन टर्ममा चाहिँ एकचोटि मात्रै 1 आउने थियो नि त, एउटा कम्बिनेसनको लागि मात्र. म्याक्स टर्म भनेको जस्ट अपोजिट हो क्या. यसमा चाहिँ के हुन्छ भन्दाखेरि एकचोटि मात्रै 0 आउँछ. ट्रुथ टेबल बनाउने हो भने ए र बीको लागि एकचोटि मात्रै 0 आउँछ, बाँकी सबैमा 1 आउँछ क्या. अर्गेटमा के हुन्छ त त्यही हो नि त होइन हो. दिस इज एक्ज्याक्टली द सेम कन्सेप्ट. एक्ज्याक्टली वान ट्रुथ टेबल रो as output 0 and every other rows have the output 1. Therefore, a max term identifies a unique row where the output is 0. This makes max term the building blocks of POS expressions. POS भनेको के हो भन्दाखेरि product of sum. यहाँ के छ त हाम्रो यो this is one sum, this is another sum, this is another sum, this is another sum. So we can multiply each of this sum, which is also known as product of sum or POS. The expression looks like a plus b multiplied by a plus b complement multiplied by a complement plus b complement and similarly. Okay, now if the input is 0, you have to write a, and if the input is 1, you have to write a complement. This is an important thing and most of the students often confuse at this point, so please pay close attention. For min terms, 0 means complemented variable and 1 means normal variable, but for max terms, 0 means normal variable and 1 means complemented variable. Okay, so basically 0 means a plus b, because 0 means non-complemented normal variable and 1 means complementary variable. Here in second case 0 1, there is 0 1. 0 means non-complemented variable and 1 means complementary variable. This is only for max term. Okay, don't confuse it for min terms. And here you can see 1 means complementary variable and 0 means non-complementary normal variable. 1 means complementary variable and another one which is for b, it is complemented variable. This is important concept for SOP. Okay, we have also studied that max term is opposite concept to min terms, right? And we have also studied De Morgan's law. De Morgan's law is simply a relationship between the AND gate and OR gate. So there must be a relationship between max term and min terms, because min terms means there are AND gates and max term means there are OR gates. So there must be a relationship between min terms and max terms, meaning we can do the same work. That means we can get the same output as min terms by using opposite gates, which can be implemented using De Morgan's law.